Alright, today in this video we're going to talk about how to determine whether different series converge or diverge. And so we're going to start off with two very simple sequences. And the first is the summation from n is equal to 1 to infinity of 2n plus 1. And the second one is the summation from n equals 1 to infinity of 3 over 2 to the n. Now, first, let's make sure we understand what some of the symbols are. This is your expression, and n equals 1, that is your term number, and that number you're going to plug in for n. And this symbol right here kind of looks like an S. It is the Greek letter sigma, which means to sum. So this is going to mean you need to sum up all of the values that you get by plugging in the term number. So when n is 1, you get 2 times 1, which is 2 plus 1, that is 3. Plus, when n is 2, you get 4 plus 1, which is 5. When n is 3, you get 6 plus 1, which is 7. And you can see this is the expression for odd numbers. So 3 plus 5 plus 7 plus 9 plus 11. Well, let's see. We already have 8 plus 7, that's 15. 15 plus 9 is 24 plus 11. Hey, you can see that this thing is a snowball rolling down the hill, and all it's doing is accumulating more and more and more. And if we continue to add more terms to this, the sum is just going to go towards infinity. So this is an example of a series that diverges. Okay, now we're going to take a look at this one, and we're going to plug in 1 for n, and we're going to get 3 over 2 plus 3 over 4 plus 3 over 8 plus 3 over 16 plus 3 over 32 plus ... All right, so you can see here that the numbers are getting smaller and smaller and smaller. And so eventually you're going to have, let's say, 3 over 2 to the 30th. And so 2 to the 30th is going to be a really, really big number. And 3 over that number is going to be a really, really small number. And when you take that really, really small number and add it to the sum of all these numbers and the ones that came between it, this number is negligible. Negligible. It really doesn't make much of a difference in the entire sum. And so eventually this is going to converge. All right, now we might as well talk about it right now. This is called a geometric series. This is a geometric series. And a geometric series is a series that in order to get the next term in the series, you need to multiply the previous term by a common ratio. So we can see here that our first term is 3 halves, and our common ratio is simply 1/2. And you can kind of convince yourself that that makes sense. 3 halves times 1/2 is 3/4. 3/4 times 1/2 is 3/8. Half of that is 3/16, so on and so forth. So the formula for a geometric series, and to find that what the sum is going to converge to, the sum is equal to a1 over 1 minus r. a1 is the first term, so that's going to be 3 halves over 1 minus 1/2. So that's going to be 3 halves divided by 1/2. And so that, when you flip and multiply, that's just going to give us 3. So this sum is going to approximately be converging to 3. And so that is how you find what a geometric series converges to. Now, this formula right here, you can only use this when the absolute value of r is less than 1. In other words, when you're multiplying by numbers that are smaller than 1. That's the only way that the terms way out here are going to approach 0. And so you need to be careful to make sure that you only use this formula right here when the common ratio that you're multiplying by is less than 1. If it's bigger than 1, then clearly the number is going to be getting bigger, 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 and it's going to be that snowball rolling down a hill, collecting and accumulating more terms. So far, we've looked at two different types of series. One is an arithmetic series, and that is simply when you're adding the same term each time. Let's say in this example, you're adding 2, adding 2, adding 2, and we've already established that these are always going to diverge for obvious reasons, because if you continue to add, or subtract the same amount, well, it's just going to be a snowball rolling down a hill. All right, and then we also looked at a geometric series, and we established that if r is less than 1, it's going to converge, but if r is greater than 1, it's going to diverge. But the question is, what do we do when we come across a series that is not arithmetic and it is not geometric? What do we do? For instance, like 1, 4, 9, 16, 25, 36. Actually, if they had pluses in between this, it would be a series. This is not geometric because you're not multiplying by the same thing every time, and it's also not arithmetic because you're not adding the same each time. And for that, we are going to learn 10 different tests for convergence and divergence. Today in this video, we're going to focus on the geometric series test and the nth term test for divergence. And then we're going to look at the telescoping series test, which is not covered on the BC exam, however, it is helpful to know. And then the P-series test, that's pretty easy. The integral test, that's not bad. And alternating series tests with error bound, direct comparison test, limit comparison test, ratio test, and root test, which is also not covered on the BC exam. However, it makes things easier in certain problems. So that is where we're headed, and today we're going to start with the geometric series test and the nth term test for divergence. Okay, the first test that we are going to look at is called the geometric series test. And a geometric series is written in this form: the summation from term number 0 to infinity of a1, which is the first term, r to the n, or n equals 1, or it could be n equals 2, n equals 3, n equals 4. And you have to be very careful about the way this is written, because it is easy to think that the first number that you see is always the first term. All right, and that is not always the case. You need to plug in the first term number into the expression to figure out what a1 actually is. If you're multiplying by something less than 1, as we've said, it is going to converge, and the sum that it's going to converge to is this formula here: S equals a1 over 1 minus r. If it diverges, you don't do anything, you just say it diverges. So let's take a quick look at these two real quick. N equals 1 to infinity, 3/2 to the n. Now this is my r, and we clearly can see that 3/2 is greater than 1. So immediately when we see that, we can deduce that this series is going to diverge, because once again, you're going to be multiplying by numbers bigger than 1. This sum is going to be getting bigger and bigger and bigger. So that's going to diverge. So you don't even have to do anything with that one. Now this one, we see that our r is 2/3. So we are multiplying by something smaller than 1. So this is going to converge. Now the question is, what is it going to converge to? What is the sum of terms 3 to infinity? Well, let's just first see what a1 is. a1 is what you get when you plug in 3 into this formula. So 3 minus 1 is 2. So we're going to have 5 times 2/3 squared. And so that's going to be 5 times 4 over 9. And so we're going to have 20 over 9 as our a1. And so we can see there's an example where it's very misleading, because 5, which is the number in front of the parentheses, is not our a1. You've got to plug in the first term number to get a1. So we know it's going to converge, so let's see what it converges to. So the sum is equal to a1, which is the first term, 20 over 9, divided by 1 minus r. and r is 2/3. So we end up with 20 over 9 divided by, well, 1 minus 2/3 is simply 1/3. So we're going to have 20 over 9 times 3 over 1. That's just going to give us 60 over 9, and we can divide both of those by 3. So that's going to be 20 over 3, and that's going to be the sum that it converges to. All right, two more examples here on the geometric series test. Here we have one that it's not so obvious what r is and whether it converges or diverges. So what we need to do here is we need to break up the bottom into 3 to the n times 3 squared. And we remember that the property of exponents is when you have the same base, 3 and 3, you add the exponents together, n plus 2. So the same thing works in reverse. If you have 3 to the n plus 2, you can break it up into 3 to the n times 3 squared. And 3 squared is just a constant. That's just 9. So we're going to take that and we're going to bring that outside of the summation. And so we're going to write this as the summation from n equals 1 to infinity of pi to the n over 3 to the n. And then we're going to go backwards again, and we are going to write this as 1/9 n equals 1 to infinity of pi over 3 to the n. Now once again, make sure that makes sense to you. Anytime you have an exponent that's outside of the parentheses, each thing in the parenthesis must get separately raised to that exponent. And so if we were going forward, we would take the pi and raise it to the n power, and then we would take the denominator 3 and raise it to the n power. But if you already have it in that form, then you can go backwards and write it as pi over 3 to the n. Now we're going to write this as 1/9 summation n equals 1 to infinity, and we're going to write this as 3.14 over 3, because then maybe it'll be a little bit more obvious what our r is. Well, 3.14 over 3 is clearly a number that's bigger than 1. So our r is bigger than 1. That means automatically that this geometric series is going to diverge. All right, let's move on to the next example. And we have here 3 to the n plus 2 to the n over 6 to the n. Once again, not so obvious what it's doing. Make sure you don't make this numerator 5 to the n, because you can't do that whenever you're adding exponential functions. So we're going to have to break this up, and we're going to have to divide the 6 to the n into the 3 to the n, and then we're going to divide it into the 2 to the n. So we're going to write this as 3 to the n over 6 to the n plus 2 to the n over 6 to the n. And we're going to use that same little trick that we just did a moment ago. We're going to write this as 3 over 6 to the n, and then this is going to be 2 over 6 to the n. And we can reduce these fractions, so it's going to be 1/2 to the n. And I'm going to go ahead and write the summation from n equals 3 to infinity. And then we're going to, well, let me put parentheses around this. And then we're going to have the summation from n equals 3 to infinity of 1/3 to the n. Now clearly both of these are going to converge, because 1/2 is less than 1 and 1/3 is also less than 1. So this is going to converge. So we need to figure out what these two individual sums are and then add them together, and that's what the overall sum is going to converge to. So we'll continue this up here. The first term, you got to be careful once again. If you plug in 3 into your formula, you will get 1/8. So our A1 is 1/8 over 1 minus r. R is 1/2. And so we end up getting 1/8 over 1/2, 1/8 divided by 1/2. And that's just simply going to be 1/4. Because you flip and multiply, and you will get 1/4. Working with the second one, you plug in your 3, and you end up getting 1/27. So your A1, so let me write that down here. The first A1 over here was 1/8, and here our A1 is 1/27. So we have 1/27 over 1 minus our R, which is 1/3. So it's going to give us 1/27 divided by 2/3, which is the same as multiplying by 3/2. And so we see that we're going to end up getting, well, this 3, and then that can reduce to 1/9, so 1/18. So now we need to add together 1/4 and 1/18. So it looks like the common denominator is 36. So we are going to multiply this by 9 and this by 2. And you're going to end up getting 9/36 plus 2/36. And so the sum will converge. Let me write that down. It will converge to 11/36. All right, the last test that we're going to learn today in this video is the nth term test for divergence. And the nth term test for divergence simply says that if you look at the nth term, which would be, let's just say, the 100th term or the 1,000th term or the 1,000,000th term, you go all the way down the line of terms, and if that last term, or if the nth term is not equal to 0, then automatically the series diverges. So earlier we saw the series 3 plus 5 plus 7 plus 9 plus 11. And if you keep going, you may get down to 2,000,001. Well, this last term is not 0, which means the terms are getting bigger, which means the sum is getting bigger, which means it's diverging. All right. Now, it's important to understand something with that. This does not mean that if the limit equals 0, then automatically the series converges. This test can only be used to prove divergence. If the limit equals 0, then you must use another test to determine convergence. So that's very important. Very, very important. Put a star on that on your notes. Make sure you understand that. This test can only be used for proving that a function diverges. But if the limit equals 0, then that doesn't mean anything. You cannot use this test. You have to use a different test to determine whether it converges or whether it diverges. All right, 3 quick examples here using the nth term test. And we are going to take the limit as n approaches infinity of this number, this function rather. So when you plug infinity in, this is similar to finding the horizontal asymptote. So we know that anytime you're letting n approach infinity of a function like this, you are simply going to compare the powers. Well, that's n to the first, and that is n to the first. So therefore, you are going to use the coefficients 2/3. And so the limit as n approaches infinity of a sub n is going to equal 2/3, which is not equal to 0. Therefore, this series diverges. All right, the second one, n factorial over 2n plus 1 factorial. Well, once again, we're going to take the limit as n approaches infinity of a sub n. And when you do, this 1 is negligible. All right, so then essentially what you have is n factorial over 2n factorial. And so these are going to cancel, and you end up with 1/2. 1/2 is not equal to 0, so therefore this series diverges. All right, the third one. Once again, we are looking at letting n approach infinity. And when you do that, this term is going to be negligible. And so, therefore, we end up getting the limit as n approaches infinity. We end up getting 3 to the n over 3 to the n. And that's going to equal 1. 1 is not equal to 0. So, therefore, this series diverges. This is the easiest test out of all 10 to apply. So, normally, this is the one that you want to apply first, because a lot of times you can try some of those other tests that we're getting ready to learn in the next few days, and you will get all bogged down with it when you could have determined that it diverged very quickly by using this very simple test, the nth term test for divergence.